Hi everyone, so in this video we're going to be looking at the differences between heat and temperature and the temperature changes that occur during endothermic and exothermic reactions. Now when we look at heat is one form of energy, and during chemical reactions energies flow in and out of reacting vessels. Now inside the reacting vessel is known as the system, and outside the reacting vessel is known as the surroundings. So if you look at these diagrams, inside the boxes here, this is the system, and outside is the surroundings. Now there's three types of systems. There's open, closed, and isolated systems. Here you have an example of an open system. In an open system, matter can go in and out, so there's transfer of matter and there's transfer of energy. In a closed system, you do not have transfer of matter, so matter stays inside the system. It's only energy that can be transferred. But the total energy of the process will not change, because according to the law of conservation of energy cannot be created or destroyed. So there's only transfer of energy in a closed system. And in an isolated system, there is neither matter goes in and out or energy goes in and out. So there's transfer of neither matter or energy. Now, if I were to put the systems into context, I would use an open cup like this for the open system. So where matter goes out here and heat goes out. So the matter is in the form of the vapor from the cup. And this would be a closed system where you're blocking any matter being transferred to the surroundings, and there's only energy that is transferred. And an isolated system would be a vacuum flask where there's nothing transferred. Now, since we're talking about heat transfer, let's see the difference between heat and temperature. By definition, heat is a total kinetic energy of particles in a substance. So it is, like mentioned here, total energy available in the system. Heat takes into consideration the amount of substance that you have, the volume or the mass of the substance. And heat has symbol Q. Q has units joules or kilojoules, because this is a measure of energy content. Temperature, on the other side, temperature measures the average kinetic energy of the particle in a substance. It does not take into consideration how much of the substance you have. So it's just going to tell you how hot or cold a substance is. And as you know, temperature has unit degrees Celsius or Kelvin. Considering the example here where you have water in a beaker at 100 degrees Celsius, and I'm taking a pipette from this hot water and I spill a few drops on my hand. Now, yes, it's going to cause some burn, it's going to cause some damage to the skin, but the damage caused here is going to be much less than if the whole beaker spills on your hand. If the whole beaker spills on your hand, it transfers a large amount of heat to the skin, which causes severe burn. But here, because you have a small drop of water, the amount of heat that transfers to your hand, to your skin, is much less. So the damage goes to the skin is much less in here than in here. But both water are at the same temperature. But heat takes into consideration amount of substance, while temperature does not take into consideration. It's just telling you how hot it is, how cold it is. So basically, it's a measure of the average kinetic energy. So you have the essence of the explanation here, where it tells you that temperature measures the intensity of the heat, while heat measures total amount of energy. Let us now see endothermic and exothermic reactions. Now, heat, we called heat Q, Now, how much heat something contains is called enthalpy. Now, the difference between heat, Q, and enthalpy has symbol H here. It's very simple when you look at it in terms of the unit. Heat is energy and it has units kilojoule or joules, while enthalpy has units kilojoule per mole or joules per mole. So both heat and enthalpy measures energy, but enthalpy is energy per mole of substance. Now, when a reaction occurs, heat content will change. When heat content changes, enthalpy changes. And in science, change is denoted by delta. So delta H is enthalpy change. And an enthalpy change can be positive or negative. And there's two types of reactions. When heat is liberated, where you have exothermic reactions, and during exothermic reactions, delta H is negative. And when heat is absorbed, that is endothermic reactions, delta H is positive. Let's see in a little bit more detail exothermic reactions. In an exothermic reaction, energy is liberated to the surroundings. So energy goes to the surroundings. So the surroundings will have more energy than the system. So if we take an example, let's say reactants have enthalpy 100 kilojoules per mole. When these reactants undergo an exothermic process, we find that energy is liberated to the surroundings. So 75 kilojoule per mole will be going to the surroundings, which means that the product only has 25 kilojoules per mole left. So there is energy liberated to the surrounding, which means that the energy level of the system is going to go down. So if this is energy, and here you have reaction progress, you see that the reactants have more energy than the products. Why? Because the energy has been liberated to the surroundings. So enthalpy change will be a drop. So enthalpy change is negative. So there is a drop of 75. So minus 75 kilojoule per mole. Now, if you look at temperature against time, you will see that in an exothermic reaction, temperature will increase with time. So here, reaction hasn't started yet. As soon as the reaction starts, temperature goes up, and when the reaction is over, temperature is going to go back to room temperature. Now, if we consider endothermic reactions now, endothermic reactions, this is when heat is absorbed from the surrounding. One example is photosynthesis, where energy from the surrounding is absorbed by the leaves to be used to make chemical energy, that is the food. So here, energy is absorbed from the surroundings, which means that the temperature of the surroundings will drop. So here, when the reaction hasn't started yet, it's room temperature. Temperature drops and then we'll go back to the room temperature. So this is temperature against time for endothermic reactions. Now, if we look at the energy levels, let's say we have reactants that have energy, that have enthalpy 100 kilojoules per mole. These reactants gain energy from the surrounding. Let's say it gains 75 kilojoules per mole from the surroundings. So then the product is going to have more energy. So the product H will now be 175 kilojoules per mole. So you can see that delta H is positive. There's an increase by 75 kilojoule per mole. So this will be the delta H. So if you draw the energy profile diagram, you can see the positive delta H for an endothermic reaction. Let us now see how we draw energy profile diagrams. This is an energy level diagram, so you can only see the levels of the energies. In an energy profile diagram, you will have the reaction coordinate x, or the reaction progress, and on the y-axis you're going to have potential energy or energy. And you will also need to include activation energy, where it's the energy from the reactant to the transition state. So it's always from the reactant to the peak. Let's see energy profile diagram for an exothermic reaction. So you're going to have your axes, you label them properly. So you have reaction progress and potential energy. In an exothermic reaction, energy is lost to the surrounding. So you're going to have levels of reactants and products as such. Now I will also show the activation energy. So you will have a peak here, and the activation energy is from the level of the reactant to the highest point, which is here. And because this is exothermic, I will also show the delta H being negative. For any values that you know, you include the values in the energy profile diagram, like here and here. And if you know any of the, let's say you know the reaction equation, so include the actual reactants and the actual products here. And if you know the energy level of the reactants, energy level of the products, you can also include it. Now, one more thing about exothermic reactions, you have to know that a reaction that involves combustion and involves bond formation is exothermic. So when you do combustion, temperature increases, and when bond formation occurs, energy is also liberated to the surroundings. If we now look at the energy profile diagram of endothermic reactions, I will again start by my axis. And because you have energy that is absorbed from the surroundings, you're going to have reactants at lower level and products at higher level. I will connect using the peak, and you will have activation energy that goes from the level of the reactants to the peak. And I will also have my delta H, which goes from level of reactants to products, and delta H is positive. Now, it is important to know that when you look at the levels, at the potential energy, lower the level, the more stable. So if you look here, in an exothermic reaction, the product is at a lower level of potential energy. Therefore, the product is more stable. And if you look at an endothermic reaction, the reactant is at a lower level, so the reactant is more stable, and the products is less stable. This makes exothermic reactions more probable to happen because the products are more stable. And one additional information about endothermic reaction, it involves photosynthesis, where energy is absorbed, and it also includes reactions where you have a lot of bond breaking, where a lot of energy is spent in bond breaking, because to break the bond, you need to supply energy. So you need to absorb energy from the surroundings to provide an effort to break the bond. Bond breaking is an endothermic reaction, and bond formation is an exothermic reaction. This is important for you to remember. Using this understanding, you're going to try this question, this one as well, on the next page. And you will go to the homework section on page 17, and you will do these 4 MCQ questions. Answers to these questions will be in the next video.